Our next speaker is Michael Ma, who worked with Mr. Ari Lee and Professor Jan Egedal at MIT. He will speak on electron dynamics in a three-dimensional asymmetric magnetic reconnection plasma simulation.
All right, so good afternoon, everyone. So today I'll be talking about plasma. And no, despite a common misconception, I'm not going to be talking about blood. I'm going to be talking about the fourth state of matter, which is actually really cool. So, what is plasma? Plasma is often defined as a quasi-neutral ionized gas composed of positively charged ions, negatively charged electrons, and neutral gas atoms. And what I mean by quasi-neutral is that the number of positive and negative charges are approximately equal. And it is known for exhibiting collective behavior, which basically means if something happening at this end of the plasma can affect the behavior all the way at the other end of the plasma. In a laboratory setting, plasma can be created using an electric field, which is usually generated by two parallel electrodes. And what happens is that the free electrons in the gas gets accelerated by this electric field. And then this collides with the neutral gas atoms. So then electrons get knocked off these gas atoms and the process repeats. When this happens over and over again, a plasma is eventually generated. And this ionization chain reaction is called an electron avalanche, and that's shown here. Okay, so my study focused on a certain phenomenon in plasma called magnetic reconnection. And basically what happens in plasma is that there's this current sheet across the plasma, and across the two sides of the current sheet, the magnetic field changes direction. And when the reconnection process occurs, this current sheet breaks into bar-shaped filaments. And the reconnection occurs in the gaps. And in this, you can see reconnection happening here with the field lines coming toward each other. And the filament would be here and here, and the reconnection is occurring there. So by now you must be wondering why you would even care about this phenomenon you never probably even heard about until today. So I guess just let me tell you a story. On October 29th, 2003, reconnection occurred in the Earth's magnetosphere, and the induced currents that resulted caused the power grids in Northern Europe to fail, and high radiation levels forced all the airlines to alter their high latitude routes. On that day, the communication systems, most of them were disabled, and the same with global positioning systems. In addition to all of this, reconnection is also a major problem in the production of energy through nuclear fusion. So what my study is trying to do is to see what's actually happening during the reconnection process, because currently in three-dimensional plasmas, the internal magnetic and electrical structure is not known. We only know that for 2D. And so computer simulations are often used to analyze plasmas, and out of all the many types, the particle and cell, or PIC for short, simulation has shown to be particularly successful. And what it does is that it computes the orbits of a large number of charged particles, and then from that it can calculate the charge and current densities. Although it does not approximate any basic physics, the computational limitations do necessitate that some of the physical parameters be compromised. For example, the proton to electron mass ratio is often reduced from 1,836 to around 200. And this can actually reduce the computation time for some computers from 5 years to about a week. So in two-dimensional plasmas, something called the acceleration potential has been created to parameterize the effect of the electric field. The acceleration potential usually develops to control the electron density and maintain the quasi-neutrality, and is often denoted as phi parallel, and the definition is shown here. And the acceleration potential is often called a pseudo-potential. And this is because that when phi parallel is multiplied by the charge of an electron, it measures the work done when an electron exits or enters the reconnection region in a single shot along the field line. The equations of state, which relate the components of pressure and the density without referencing the potential U have also been created for two-dimensional plasmas. And in these equations, f of x, like here, is a function which represents 1 over 1 plus x. And these are the components of pressure, and n is the density. And what these equations assume is that the plasma is symmetric in the y direction. And this, unfortunately, in naturally occurring plasmas, this is simply not true. All the data for my study was from a VPIC simulation conducted at the Los Alamos National Laboratory by a supercomputer called Roadrunner. And most of the data analysis was done on a program called MATLAB. So after tracing thousands of field lines, it was discovered that the general shape of the field lines only changed really minimally in the y direction. So we can analyze the data in 2 slices instead of 3 or more. So if you look here on the left, this is one of the slices called vertical slice, which shows the inflow section of the plasma. And then on the right is the exhaust section of the plasma. And when you actually combine these 2 slices, it actually looks really similar to the 2D plot, which is shown here. So using interpolation, we were able to calculate the component of electric field parallel to the contours of the magnetic field lines. And when we integrated this value, we were able to obtain phi parallel. And phi parallel is shown graphically here. And the colors represent the magnitude. And if you look, and it was actually really different from what we expected. Because from the 2D data, we expected that phi parallel would turn out to be uniformly 0. And then as you see here, that's clearly not the case. If you look in the middle of the graph, you can see that the colors are blurred vertically. And what this probably means is that there's a plasma wave propagating through. And this is probably partially responsible for why phi parallel isn't uniformly 0. But the main reason is probably simply because 3-dimensional plasmas are not as rigid as 2D plasmas. So field lines can just stray throughout the whole plasma. Scatter plots comparing the components of pressure to the density were also created for certain field lines. In these plots, the red points are the ones predicted from the equations of state, while the blue points are the ones calculated numerically from the simulations. And if you look at the graph on the left, which shows the parallel pressure, the points actually curve up. And this is due to electron heating. But about seeing how much the red and blue points overlap shows that the equations of state actually work pretty well in 3D. But for some of the field lines, this just wasn't the case. So for very few of the field lines out of the thousands we looked at, it turned out like this. And the equations did not fit the field lines that well. And you notice what's unique about this, the blue points on this plot, is that it changes sharply in 2 locations. And this was really unexpected. Because in plasmas, electrons are highly energized, so they're moving at extremely fast speeds along these field lines. So for the pressure to just change suddenly was something that we never observed before in a 2-dimensional simulation, and something that we did not expect to see. So after that, we decided to calculate the parallel pressure to perpendicular pressure ratio. And we did this for both the equations of state and the actual simulation data. And then when we looked at the two, this shows the XZ plane, and now it's being stepped in the y direction. So if we look out through the whole plasma, the 2 figures are practically identical. And that shows that the equation of state actually fit the 3D plasma really well. So just to wrap up, although we were not able to compute the acceleration potential felt by the electrons that well, we were able to verify the equations of state in 3D. And we also discovered that the electron pressure can just change suddenly in 3D plasmas, which will probably be the object of future research. So lastly, I would like to thank my mentor, Professor Jan Egedal, as well as all the graduate students in this lab, especially Mr. Ari Lei, I'd also like to thank my tutor, Dr. Jenny Sindova, as well as all the RSI staff and students. I'd like to thank CEE and MIT for making this research opportunity possible, as well as all my sponsors. And thank you for listening.
Are there any questions for Mike? Mr. Holt?
Can you think of a classical phenomenon where you might see that jump in pressure versus density?
So the question is, if I can think of a classical phenomenon where we see this jump in pressure in relation to density. And I actually pull up all the field lines that show this behavior, and it's only a certain few, and I actually graph them in a simulation box and compare them to all the other field lines. And what I saw was that these certain field lines actually went from the bottom of the inflow section of the plasma through the exhaust and then to the top. And this is something in the rigid 2D plasma you never see. And this is probably the reason, just because it's straight through different sections of plasma where the densities are actually different, because this is asymmetric plasma. So the density here was greater than density here. So the fact that the field line actually went through the whole plasma through 3 different sections probably caused the sudden changes in pressure.
Professor Kishani?
There's a key parameter in plasma which is called the Debye length. I don't know if you've heard about it. So that should be the distance if I put a point charge in the plasma when be masked by the electron going toward it. It's a distance in which the electric field of this charge is felt. And I wonder if that typical distance plays a role in this phenomena and how it is compared to the typical spatial measures of the features you see in the simulation.
The question was how the Debye length affected sort of the simulation and the phenomenon of magnetic reconnection. And actually, at our lab, I don't think we really considered the Debye length that much. We don't really examine how much if changing the length actually affects reconnection. We're more just into the field lines, seeing how the field lines interact and the electron trapping in the reconnection region. So.
Dr. Baganoff?
Can you explain why changing the mass of the proton speeds up the calculation?
Okay, so changing the mass of the proton to electron mass ratio is not just changing like a big number to a small number. Like that doesn't really affect the length of how long computation would take. But actually what happens is that since we reduce this mass ratio, the number of actual data points that was actually tested by the computer was reduced. And then by reducing the number of data points, so it significantly reduced the time. It's sort of just scaled down the experiment, really.
Why does it reduce the number of data points?
Basically, the particle in cell simulation looks at divides up the whole simulation box into cells, and in each cell, it looks at the particles inside and computes all the values for it. And by reducing the ratio, I believe we're actually looking at less particles in the cells.
Dr. Stefanski?
So in the simulation, could you talk a little bit about how the simulation was carried out? Did you divide things into a grid? Did you use an adaptive mesh refinement algorithm? Could you talk a little bit about the simulation algorithm?
Well, the VPIC simulation, the question is about how we conducted the simulation. And the actual VPIC simulation was conducted at the Los Alamos National Laboratory on their supercomputer. So I wasn't actually involved in the actual,
At what point did you join this project?
So when I joined the project, they had the data on about 2 trillion particles, and they needed to analyze it. But what we're also doing at the Plasma Science and Fusion Center at MIT, you can sort of see here, this is a picture of the VTF, or Versatile Toroidal Facility. And there's this little like grid thing you can't really see well, but we're building these in our setup facility, which actually would experimentally like be a particle, looking at the particle and cell data experimentally. Like each of these are grids with cells in them.
Okay, let's thank Michael.